Hi and welcome to the SHA1 Performance Quest episode 5. This time I'm returning to the all-knowing narrator style, so no special story happening here except for us trying to get most out of our current SHA1 implementation. That said, let's get started with some benchmarks. 154 megabyte per second, come on. Okay, that's kind of worst case because we feed 10 bytes at a time. So 185 is what we get in a common case when bigger chunks are fed. That's not too bad, especially considering that we have started at a mere 120 megabyte per second when this project has been touched for the first time. Where to start? Right now we're seeing the output method, which is basically just called at the end of the entire hashing operation. I guess that's not where we would find our resources spent here. What does SHA do? I mean, at the end, sure, we basically take the state and convert it into 20 bytes. But before that, when you feed it data, it will chunk up the data into 64 byte-sized chunks that are then handled by some routine that basically does a lot of work on them, byte by byte, I guess. Or no, integer by integer, if I'm not mistaken. Therefore, we should put our attention all into the internal processing block method where we are right now. And just before we do anything, it's worth noting that we will definitely make this beautiful code more ugly and less maintainable. That is kind of what happens. It's this weight between maximum performance and maximum maintainability. And usually these two are not the same, not at all. While looking at this process block method, I think the best way to optimize performance is to try to unroll loops and reduce conditionals to the point where they ideally just don't exist anymore. Something else to look at would be function calls, because these are actually quite expensive as they involve so much work around the program stack. Looking at our code here, we see that there are quite a few small functions, ff, gg, hhii, and I do wonder if they're actually in line, thus there is no real function call, or if these are actually called. I mean, every optimizer in the world will probably just make these small tiny scriptlets or function bodies in line, right? But I don't see it specified there. It either happens automatically or it doesn't happen at all. And I just want to know. So the first thing I do here, because it also seems most simple, is to make sure these functions are definitely in line. Doing this in Rust is quite straightforward and simple, because above each item you can basically tell the compiler what to do with it. And if the item is a function, you can say inline always to basically force it. I mean, you don't force the compiler, but you tell it real hard to goddamn inline these. If you possibly can, make it possible. And this is what I'm doing here. And as we can see in the results, it actually doesn't change a thing. This either means that the function calls are not expensive at all, so even if they are now inline, it doesn't change a thing, or they have been inline before. And you know what? I think it was the latter. So doing this is not the way to improve anything here. The next best thing to do, and the thing that is a bit, let's say, more elaborate, is to unroll this loop. As you can see, it's a tight loop. Well, it's a loop above 80 elements. And there's a match case in there that will be equivalent to some if condition. And having a complicated if condition like that, where most of the branches are actually unused within a loop like that, is a big waste of cycles, even though, of course, it's very readable, right? You see exactly what's happening here, and that makes the code very maintainable. So I do like the code from a maintenance standpoint, but from a performance standpoint, you don't really want that. So all I'm doing now is copy-pasting the entire loop there and making sure that I adjust the ranges to call the right function at the right time. And yes, copy-pasting code usually indicates that you have a problem, but sometimes, you know, it solves a problem, at least when it comes to performance. Again, code is usually not getting better if you try to get the maximum performance out of it. And personally, I believe that most of the time it's not worth it unless it's something like a hasher, which is just supposed to do this the entire life, you know, that's its purpose. It's supposed to hash bytes. And, you know, if it means that the code is less maintainable, but also that it's the fastest thing on earth, then I'm totally fine with the code being less maintainable, because if it works once, it will always work, in the sense that you don't touch that thing ever again. I mean, you are not really likely to touch it again, ideally. Otherwise, well, it's expensive. All right, now that the grunt work is done, let's have a look at the results of our hard work. Anytime now, it's gonna happen. Wait for it, and oh yeah, there it is, 242 megabyte per second. That's just 160 megabyte per second away from the magic marker 400. Which is what SHA1 sum does on my system. Entirely written in C and I guess highly optimized. But Rust can do it, right? Yes, Rust can do it. So let's go ahead. Something must give us 160 megabyte per second performance, and I wonder what that could be. I mean, one thing comes to my mind, right? Whenever I see an index operation in Rust, I know that, ooh, it's probably quite expensive. Why is it expensive? Because of the bound checking that happens all the time. And in our case, the loop goes from 0 to 80 always. And the index is thus kind of fixed to a valid range. And I do wonder if the compiler is able to realize that, so it takes out the check. After all, we are not accessing a vector, we are accessing a standard array. The only way to get around these boundary checks is to use unsafe code. Unsafe because, well, it's not checked anymore, and we can basically trigger a segmentation fault by accessing wrong memory. Also, Rust can't make sure anymore that you don't use this memory elsewhere, and you know, you get all kinds of issues that you get with other programming languages if you use all the means possible in unsafe code. Here it's nice and self-contained. The only thing we want to do is access this array through pointers to get rid of these index-related boundary checks. Again, you know, the compiler could possibly figure that one out and realize, it won't overflow, so in that case I can take out these boundary checks, but it's something that happens under the hood and the compiler doesn't really tell you about it, so either we hope that it will do it, or we do it ourselves, and this is what's going to happen here. It's worth noting that in Rust you cannot use the common pointer arithmetic that you know from C and C++. You have to use the very explicit offset method, and I think that's really what it is about. They want it to be explicit. Some thoughts about that right now that we are here. I'm not sure if that is the most efficient code that you can possibly write. Because we have, I mean, it's just the way we write it, right? We have an extra addition here. We say bi plus 1, 2, 3, and then this is multiplied by the amount of bytes per items, and then this is added to the pointer. So worst case, we have 2 adds and 1 multiplication. If we would do everything ourselves, we could say, well, we put the pointer to the right spot and use it, then we just offset it by 1 item. And as an item size is known at compile time, the compiler knows, okay, if you offset it by 1 item, you offset it by 4 bytes, for instance. And then we use the pointer again, and then we offset again, and so on, which would be exactly 1 add and not 2 adds and 1 multiply. Question is, does the compiler actually optimize that for us? I would hope so, because it's quite obvious what's happening there. But, you know, you don't know. That's the thing. But I don't bother here either, so it just stays as it is. 2 adds, 1 multiply, worst case. Maybe just 2 adds. Who knows? So here it comes. I thought it would be easy to implement this offset thing, but it turned out it's not. Well, it is if you know what's happening. In C, pointers to arrays are automatically cursed to pointers to the first item of the array. So you can use that interchangeably. It's the same thing. But Rust is explicit, right? I should know that by now. So it doesn't do that. It just tells you that some generic basically wasn't implemented. I mean, if a generic doesn't get implemented, then you don't know that, right? You only see in the documentation, oh, there is this implementation, but you don't realize that it wasn't implemented for you because your type was wrong. So what you have to do is get a pointer to the first element of your array, and then you're all set and fine. But without that, well, have fun. And a quick cut later, we are there where we want to be. Everything is unsafe now. Every pointer access or every access to an index is now behind an unsafe region that accesses the pointer directly. And the result of that is kind of underwhelming, I must admit, in the sense that there's no measurable improvement. This is a strong pointer, I guess, towards Rust automatically optimizing this. So if it realizes there are static ranges, it does a compile time range check and removes all the runtime range checks, which seems to be alright. But for some reason, I wasn't sure if that's truly the case or not. So I left it in and moved swiftly on. But where to? Honestly, I had no idea what else to optimize here. I mean, I did the obvious things and I managed to improve speed quite a bit, but now I had no idea. So I wanted to try out call grind, right? Call grind is Wahlgrind with the call grind or call grind tool included. And doing that was kind of, well, unexpected because it worked. But the callgrind annotate tool couldn't really tell you much because most of the methods or functions called inside were kind of unknown, and apparently the callgrind output was a bit weird, so callgrind annotate couldn't really handle that. And after all it told me that most of the time was spent in process block. Who would have thought that? And a little bit time in memset, but just a fraction of that. So yes, that was rather unsuccessful, and I still had to figure out what to do next. Fortunately, the answer to that has been in front of my face all the time. Look on the left side, there's the Go implementation, and making Rust faster means learning from the best in that case, in one of the next episodes of the SHA1 Performance Quest. Hope to see you there, and thanks for watching.